Hey there, Gregory Carlson here with the Calculus Building. So we just learned about the chain rule, and I think you're going to see these examples are pretty straightforward, so I hope they make sense. We want to differentiate the function 2x plus 5 to the fifth power. So I'm going to actually do this problem two slightly different ways, but that both use the chain rule, and you can pick whichever way you like better. So if we tried to do the product rule or the power rule, we'd have tons and tons of foiling we'd have to do. It would just be a nightmare. But instead we can do the chain rule and make this a lot easier. So what I'm going to do is I'm going to take this amount inside of here, and remember, we use the chain rule when we have a function inside of a function. And so I'm going to call the inside of this a, which means that my inside function is y equals, or I guess the outside function is y equals a to the 5. And we know that a is equal to 2x plus 5. Okay, so y equals a to the 5 and a equals 2x plus 5. And now we can use the chain rule because what we want is dy dx. We want dy dx, but with the chain rule, I can find that by taking the derivative with y with respect to a, this new variable, and then multiply that by a, the derivative of a, with respect to x. And so you can see that by making a be my in-between variable, we're going to be able to make this a lot easier. So we do dy dA times dA dx. So in other words, dy dx equals the derivative of y with respect to a is just 5a to the 4. So that's just the power rule. So 5a to the 4 right there. And we're going to multiply this by the derivative of a with respect to x. So looking over here, the derivative of a with respect to x, we can ignore the 5 right here, and the derivative of that's just going to be 2. So the derivative is just 5a to the 4 times 2, which is equal to 10a to the 4, because 5 times 2 is 10. And now we're pretty much done. All we got to do now is just plug back in a. So in other words, dy dx is equal to 10 times a, which is 2x plus 5, to the 4th. And we're done. That's the derivative. So I hope you can see that that's really nice. We didn't have to do too much work on that. We found the derivative pretty easily by just taking the derivative with respect to a and then the derivative of a with respect to x. So I don't always prefer to do it this related rates way. If you like it that way, then definitely do it that way. But here's another way to do it. What we want to do here is I'm going to kind of do this with the idea of f prime gx times g prime x. I'm going to do it kind of with this method instead of the Leibniz notation. So another way of thinking about the chain rule is take the derivative of the outside function, leaving the middle function, the inside function alone, and then multiply that by the derivative of the inside function. And so here's what that looks like. We want dy dx. So we're going to take the derivative of the outside function, leaving the inside function alone. So if we do the power rule, we bring the 5 out in front, 2x plus 5 to the 4. So you can see I just did the power rule to the outside of the function while leaving this untouched. And now we're going to multiply that by the derivative of the inside function. And the derivative of 2x plus 5 is 2. And then you're pretty much done. dy dx is equal to 10 times 2x plus 5 to the 4. So that's kind of how to do it both with the Leibniz notation and related rates, and doing it with kind of the Newton notation of taking the derivative of the outside with the inside plugged in, and then multiply the derivative of the inside. So I prefer this method, but you can use whichever method you like, and sometimes this method is a lot easier than this one, so it just kind of depends on the problem. Let's do this next one. Find the derivative of the function y equals the square root of 6 plus 9x. So I'm only going to use this second method for this one. So the first thing you want to do is rewrite this so that the square root is a power. So we're going to rewrite the function with the power of 1/2. And now let's do that process again, where we take the derivative of the outside first. So dy dx is going to equal, we bring the 1/2 out in front, leave the inside alone. And then up here is the power rule, so we're going to take 1/2 minus 1. So it's 1/2 times 6 plus 9x, and then to the power of 1/2 minus 1. And now we need to multiply it by the derivative of the inside. So the derivative of 6 plus 9x, we ignore the 6. The derivative of 9x is 9. So 1/2 minus 1 is -1/2. And so that's going to move that down into the denominator and make it a square root. So I would write the final answer as dy dx is equal to, on the top it looks like we have 9. And on the bottom we're going to have 2 and then the square root of 6 plus 9x. And that's the answer. So I know we were not supposed to leave square roots in the bottom, and in case the homework doesn't accept your answer, you may need to multiply the top and the bottom by the square root of 6 plus 9x. If you did that, you would get 9 roots 6 plus 9x. Multiply that by on the top and multiply it on the bottom, you'd get 2 times 6 plus 9x, but that's just a little icing on the cake, I think. So hopefully that makes sense. And again, as you do these, you're going to get better and better at them. You're going to see the 1/2 come down, see that that becomes -1/2, which moves the square root into the bottom. And then don't forget to multiply by the derivative of the inside, which gives us that 9 right there. So let's do another one. Differentiate the function y equals 2x squared minus 6 to the -11. Again, a classic chain rule problem. So how do you know to use the chain rule? Well, we want to use the chain rule, use the product rule when you have two things multiplying, use the quotient rule when you have two things dividing, use the chain rule when we have a function plugged into another function. That's when you want to use it. So dy dx, let's take the derivative of the outside, which would be -11 times, leave the middle alone, and then this would be -11 minus 1. And then we multiply that by the derivative of in here, and the derivative, ignore the -6, the derivative of 2x squared is 4x. And so there's your answer right there. So let's just simplify a tiny bit. That would be -44x times 2x squared minus 6 to the -12. And that's it. So you'll notice that this would have been the fraction. The initial function would have been this fraction right here. 1 over 2x squared minus 6 to the 11. So if it's written in this way, you'll want to rewrite it like this so it's in power form and easier to differentiate. And then the derivative would be -44x all over 2x squared minus 6 to the 12th. So you can see kind of the relation between the original function and the derivative. Notice the 44x comes from the 11 combined with the chain rule and derivative of that stuff. So let's finish this video with this. I promised you that I would prove the quotient rule with the chain rule. So here would be the proof of the quotient rule, which, as a reminder, if you have f over g, the derivative of that is equal to low d high minus high d low all over low squared. So that's what I'm going to prove for you right now. And to start the proof, what I'm going to do is I'm going to start with f over g prime. I'm going to do a little bit of shorthand here to save time. And I'm going to do this. I'm going to take the derivative of f times 1 over g, and then we're going to use the product rule. Okay, so here's where we're going to introduce the product rule. So that would equal the derivative of this first one times 1 over g times, and then the first one times the derivative of 1 over g. Okay, so we're trying to prove the quotient rule, so that's what we got so far. F prime times 1 over g times f times 1 over g derivative. So this first fraction is just going to equal f prime over g. So that's this right here. And now I'm going to take the derivative of this, and I'm going to use the product rule, the chain rule, excuse me. And so the derivative of that would be 1 over g prime would equal g to the -1 prime. And here's where we're going to use the chain rule. That would be -g, right, to the negative 1 minus 1. And then with the chain rule, we need to take the derivative and multiply by the derivative of g. So the derivative, this is a prime, the derivative of g to the minus 1 would be negative g to the minus 1, chain rule times the derivative of g. So in other words, that would be negative g to the negative 2 times g prime. And so that would be, I'm sorry, that should be a plus right there, not a, not a multiply, because the product rule says we add these together. And so if I do that, I get right over here, g prime over g squared, and this is negative. So I know that was a little bit tricky, but that's what it would be. This is a prime right here. And so we're almost done. Now we just need to combine these two fractions. So I need a common denominator. So I'm going to multiply this by g over g, giving me f prime g over g squared. I have a plus minus, so I'm just going to write minus g prime over g squared. Oops, and also don't forget I still have this f out here. So sorry about that. I should have had an f here and an f here. So got that little f right there, so I need to make sure I don't drop that. And you can see how we're going to get the quotient rule out of this. It's going to be f prime g minus g prime f over g squared. So that proof was, I don't know, I like that proof. Sorry, I was a little bit sloppy with it, but you see I just rearranged the order there. But you see how we can use the product rule and the chain rule with this finding the derivative of 1 over g to prove the quotient rule. So what we're going to do now is we're going to do a few more examples of combining the chain rule with other rules. And that can be a little tricky sometimes, so I'll start a new video with that. I hope this was helpful. If it was, please like and subscribe, and I'll see you in the next section.